Recording in progress.
Hello.
Hi.
Yeah, so we'll get started with your start problems, and then we could go over chapter 21 as well. Like someone requested to go over chapter 21 reactions, and we'll go from there. Okay. How are you guys feeling for the midterm this Thursday so far?
Not good at all.
Not good.
Hey, don't worry. We're all in the same boat.
Oh shoot. Oh no. Okay, let me start sharing screens. Okay. So I think you guys can follow along with these questions as well, because this is for 118C. Let's see, the start question. And why does CH3OH not do anything? Right, so for this problem right here, let's run through these. We have a carboxylic acid reacting with CH3O Na. Am I cutting off? Is my Wi-Fi bad right now, or is it like okay right now? My audio. Okay. And CH3OH. This carboxylic acid right here is a strong acid, and when it's introduced to some sort of base like CH3ONA or amine, the first thing that happens is an acid-base reaction, because acid-base reactions and intramolecular reactions are the fastest reactions that we have, are the fastest reactions, right? So CH3O minus here is not going to attack the carbonyl carbon, right? Because an acidic proton is present. This H right here is going to be attacked by the O minus instead of the carbonyl carbon, right? Because acid-base reactions happen faster than nucleophilic acyl substitution or additional elimination reaction. So the answer here is just going to be this carboxylate, where the oxygen will have a negative charge, and then the sodium spectator ion is just going to float around that minus charge right there. This CH3OH would not do anything in the reaction because this is a neutral molecule. It's a solvent. It would not do anything in the reaction, right? Because if we were to compare what's in the reagent, the CH3O minus versus the CH3OH, the CH3O minus would be the stronger nucleophile, and that's the one that we would use to react with, right? Because the negative charge is less stable than the neutral charge, making the negative charge more reactive, right? If it's less stable. Okay. Any questions on that?
How do you know? So I sometimes struggle to find out like when the acid-base reaction will occur. But basically when it's an oxygen or a nitrogen with a negative charge, that's a strong base, right? And so it will
Yeah.
always go for the hydrogen of the carboxylic acid first.
Yep. Negative
Okay.
charge on oxygen or nitrogen is a strong base, but another thing that could also deprotonate the carboxylic acid is going to be a neutral amine. Right. So if you see something like this right here, that's neutral, even though it's neutral, because the nitrogen is less electronegative than oxygen is, this nitrogen here is more willing to donate its electrons and attack the hydrogen, right? Because it's less electronegative, it is more basic, more willing to donate electrons, right? Amine here is a strong base as well that is going to deprotonate the carboxylic acid. You would expect this amine to create an amide from this carboxylic acid, right? But that does not happen if there's no heat, right? Heat is required for the conversion of this carboxylic acid to the amide. but that's not the most efficient way. Can you guys think of any efficient way that we can use to convert a carboxylic acid into, let's say, this amide right here, right? If we did NH3 excess in heat, this is not efficient. There is a more efficient way, but it's going to require 2 steps, right? Think about the reactivity of these derivatives. How can we create the most reactive derivative here? Yep, SlCO2 and ammonia, right? Where the first step is going to be SlCO2 to convert this carboxylic acid into the acyl chloride, the most reactive derivative. And once we have the most reactive derivative, we could just put ammonia excess, right? We need at least 2 equivalent. And this ammonia does not require heat because this acyl chloride is super reactive, right? It does not require a catalyst, like an acid or base catalyst. It does not require more energy like heat. It just reacts with any neutral molecule, like an amine, water, or alcohol, right? And this is the more efficient way. This way right here is not efficient because it requires more energy and more time. Not very clean, right? Okay. Let's move on to the next start problem that you had, which is going to be this right here. CH2Li, first step, CO2, second step, H3O plus. So what do you guys think this is gonna happen here? Right? If we have this reagent and these this reactant and these reagents here.
Carboxylic acid.
Yep. Carboxylic acid formation, because this is an organometallic, organolithium. Right? And this organolithium, the carbon directly attached to the lithium here is partial negative. And this carboxylic acid, carbon dioxide here is partial positive, so that's the electrophile. We attack that. We start the nucleophile, dot the electrophile, right? This is the star. Let's say this is the dot. This is the dot. This is the new bond between the star and dot. And then this dot right here is attached to a carbonyl and then O minus, right? We added an extra carbon right there, which the second step is just going to protonate the O minus to make this carboxylate into a carboxylic acid. And we added an extra carbon, right? This extra carbon right here is going to come from the carbon dioxide right there, like that, right? So now, yeah, so this is an organometallic, specifically organolithium. It's not a Grignard reagent because it's not MgBr. Okay, so the next one, it's gonna be this. 1, 2, 3, 4 carboxylic acid like this. And we are gonna react this with heat. When you see a dioic acid like this with heat, this is gonna be cyclic anhydride formation. Right, where this is gonna be the nucleophile, the starred oxygen, and this is gonna be the electrophile. We're gonna attack that, pop that up there, and we're gonna form a 1, 2, 3, 4, 5, 6-membered ring, right? Where this is gonna be 1, 2, 3, 4, 5, 6. This is the start atom. This is the dot atom, new bond. The 6 atom has an O minus, OH. I'm gonna protonate and deprotonate this at the same time. And we're going to have this OH2 plus, and then O minus, and then we're gonna go back down, kick out that good leaving group, and carbon 2 had this carbonyl still, and give us our final answer here. Right. So we attacked this carbonyl with this oxygen, giving us this tetrahedral intermediate. And then at the tetrahedral intermediate, we do the proton transfer step where we are going to deprotonate the group we want to keep and protonate the group we want to kick out or leave, right? These 2 points right here are the proton transfer steps in acidic conditions, right? In acidic conditions, these are the common steps that you're going to do for nucleophilic acyl addition elimination. Once that's ready, we kick out the good leaving group by reforming the carbonyl and kicking out the good leaving group there, making this cyclic anhydride. Okay, 1, 2, 3, 4. Okay, four more questions. Next one is going to be this aldehyde reacting with HNO3 nitric acid. This nitric acid right here is a type of strong oxidizing agent. So think of it like Jones, che118c, right? Which would oxidize this aldehyde further into a carboxylic acid, like that. Right, so did farahat go over this oxidizing agent, nitric acid?
Probably not.
Oh yeah, so I wouldn't worry about this for farahat's class, because I think this is coming from Levin's practice reaction worksheet, so I wouldn't worry about that, but you will see this again for the carbohydrates chapter 24. Can you show the mechanism for reacting a cyclic anhydride with 2 equivalent of primary amine? Yes. I will go over that after these problems and go over chapter 21 big reactions, and then at the end I'll go over that mechanism. Okay. So 3 more questions. Let's do this. Let's say we have this carboxylic acid here, and we have NaOH, water. So this goes back to the beginning of the session. Would you guys, like, what's going to be the problem here? Can I do this? What's the problem with these arrows here? Right, like we have an OH minus here and a carboxylic acid here. Think about the reactant and the properties of that reactant.
Acid base.
Yep, acid-base reaction. That's right. Because this carboxylic acid here is a strong acid. When we introduce some strong base to the reagent, to the solution, an acid-base reaction is going to happen first, not a nucleophile electrophile reaction, right? So what we're going to do is deprotonate the carboxylic acid to get this carboxylate, and the sodium ion is just going to float right next to the O minus like that, right? And creating water like that. Okay. So, okay, mechanism. You want us to go over the mechanism of this one? Wait, for this one, did it start with the ions, Camilla, or did you put the ions there?
Sorry, which letter was that?
You.
I let me check.
Mhm.
Oh yes, it did have ions.
Okay, so this right here is going to react with 200 degrees Celsius, which is high heat, right? And this high heat here is going to like overpower the acid-base properties that we were talking about. This is going to be protonated. This is going to be deprotonated because we said earlier, nitrogen is more basic than oxygen, right? Because more basic than oxygen, because nitrogen is less electronegative than oxygen. Because nitrogen is less electronegative than oxygen, nitrogen wants to donate its electrons more. It's more willing to give up its electrons, right? It doesn't want to hold on to its electrons as much as oxygen does. And because of that, this nitrogen here is going to get protonated, whereas this oxygen here is going to get deprotonated, right? But in heat conditions, like if we add enough energy, it could overcome that acid-base rule, right? So what's going to happen is that we're going to protonate the O minus and deprotonate the NH, like the ammonium ion, like this, right? So this is going to neutralize, create that neutral amine. So usually without high heat, like I said earlier in the beginning of the session right here, right? This amine right here would deprotonate the carboxylic acid to create the carboxylate in normal room temp conditions. But if we were to add heat, then we can create the amide, right? But in this example right here, because we see the amide and carboxylic acid are in the same molecule, right? This nucleophile here, the nitrogen atom, and the electrophile here, the carbonyl-carbon, is on the same molecule. This is going to be an intramolecular reaction, right? And I think this was Peter's question. Can you show the mechanism for reacting a cyclic anhydride with two equivalent with primary amine? Okay, sure. Yeah, no, this is going to be something different. This is going to form a cyclic amide from this amine and carboxylic acid on the same molecule, right? So this amine right here is going to attack that carbonyl-carbon and pop that double bond onto the oxygen right there, right? Because we are in heat conditions, high heat conditions. And that's going to give us a 1, 2, 3, 4, 5, 6-membered ring, which is going to give us this 6-membered ring here. Right, this is going to be 1, 2, 3, 4, 5, 6. 6 has an O minus now, an OH, and H nitrogen has 2 H's, positive charge. Now this is where we deprotonate the group we want to keep, protonate the group we want to kick out. Before I do that, I'm going to attach the decorations, the accessories. Right, carbon 2 has a methyl group, carbon 4 has an ethyl group. And from this point right here, I'm going to deprotonate this nitrogen and protonate the OH at the same time, right? Just to get the good leaving group I want and the bad leaving group I want, right? Okay, this is nitrogen, neutral. Everything's in place, primed and ready to go. Reform the carbonyl, kick out the good leaving group, and give us our final answer, the cyclic amide or lactam. And H, and then water, side product, right? Okay. Any questions on this mechanism? So this was an intramolecular reaction because we are forming a ring here, and the nucleophile is on the same molecule as the electrophile. And then once we get the tetrahedral intermediate, I just deprotonate the group that I want to keep and protonated the group I want to kick out at the same time. But for Farahat's test, do it one at a time, right? Like deprotonate the group first, and then protonate the group afterwards
Do
to
we,
get your preferred tetrahedral. Yeah.
sorry, do we deprotonate nitrogen at the end? Or we leave it like that?
Yes, we leave it as this because this is the neutral amide, which is its stable form. We don't want to deprotonate it because that would give that nitrogen a negative charge, which is unstable, more unstable than its neutral charge.
Okay, thank you.
Right. Yeah. Right. Okay. So last question here. And I could go over Peter's question before moving on to chapter 21 because there's a lot of things going on in chapter 21. Right. So the start question here is W. Wait, what? I think I did this already. The cyclic anhydride. Yeah. So this W here was very similar to what we did earlier. F. We have a dioic acid reacting in heat. So this is going to be intramolecular reaction, since we see our nucleophile, the star, is on the same molecule as the electrophile, right? This oxygen here is going to attack that carbonyl-carbon, pop the double bond onto the oxygen to form a 1, 2, 3, 4, 5, 6-membered ring, which is going to be this 6-membered ring right here. 1, 2, 3, 4, 5, 6. The atom 1 is still bonded to hydrogen. So that oxygen with 3 bonds has a positive charge. 2 has a carbonyl. 6 has an O minus and an OH, right? But this is the group I want to keep right here. So I want to make that into a bad leaving group. This is the group I want to kick out right there. So I want to make that into a good leaving group. I'm going to do it in farahat or in a series way where I deprotonate and protein at the same time. And the way that I can do that is use the same starting material, because that's the only like base source I have. I don't have any other like bases around where I'm going to use this carbonyl oxygen to deprotonate that positively charged oxygen to make it neutral. Right, this is just the deprotonate the group you want to keep step, which is the oxygen there. And now we're going to protonate the group we want to kick out. Right, and we formed this as a result. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. OH. Now we're going to protonate this group to give us this intermediate O minus, OH2 plus. This is the oxygen, carbonyl. Now everything is primed and ready to go. We have our good leaving group ready. We have our bad leaving group ready to stay. So we're going to kick off the good leaving group by reforming the carbonyl and driving that good leaving group off, kicking that good leaving group off, which is going to give us this final product here, which is a cyclic anhydride. Here. Any questions on this mechanism? Before, I did these 2 steps at once, right? I deprotonated this group and protonated this group at the same time. But just in case farahat wants you to do it one at a time, the only base source I have is this starting material, which is what I used as the base to deprotonate the group I want to keep, right? And then I use its conjugate acid to protonate the group that I want to kick out to make that into a good leaving group. Any questions on this? Okay. So let's go over Peter's question. Show the mechanism for reacting a cyclic anhydride with 2 equivalent of primary amine. Okay. So let's say we have this cyclic anhydride right here. And I react it with 2 equivalent of this primary amine, let's say. So cyclic anhydride is one of the crazy 2 derivatives, one of the most reactive derivatives, right? The most reactive derivatives are the acyl halide, like acyl chloride or acyl bromide, and the anhydride. Those 2 derivatives do not require heat. They do not require an acid or base catalyst as well, right? They could just react with a neutral molecule like amine here, or water, or alcohol, right? Or even a carboxylate, but that's going to talk about something else. So because we have a neutral amine right here, this neutral amine is going to attack this strong electrophile, push the double bond onto the oxygen. Yeah, did someone have a question? Okay. So this is going to be our nucleophile right here, which is going to attack this strong electrophile, this crazy reactive derivative, push the double bond onto the oxygen, and give us this tetrahedral intermediate here. Okay. Now, once we have this tetrahedral intermediate, what we could do is we can reform the carbonyl, the carbon number 1 oxygen, and kick out that leaving group right there. Right, and this is a very good leaving group because when it leaves, it's going to leave with a negative charge that can do resonance with the carbonyl. Right, so this is considered a good leaving group because it can do resonance with the carbonyl nearby like that. Right. So now the second equivalent of the amine, right? This was the first equivalent right here that we used to attack the carbonyl to create this tetrahedral intermediate. The second equivalent of the amine is going to deprotonate the positively charged amine to make it neutral. Okay. And depending on the professor or the Achieve homework program, they might want the answer in an ion like this with no acid workup, right? Because there's nothing to protonate that O minus. So this would be your final answer if there's no acid workup step. But if you were to have a second step of H plus workup, like H3O plus, then that's going to protonate the O minus into a neutral OH.
I have a
right?
quick question.
Yeah.
Why wouldn't the O minus in that structure at the bottom there get protonated by the NH2 intramolecularly?
Yes. So the O minus right here is competing as a base for this amine right here, right? And because this O minus right here can do resonance with the carbonyl, that makes the negative charge more stable, which makes it less reactive. And if it's less reactive, it's a weaker base,
I
right?
see. Okay.
And it's
Thank you.
already a weaker base because oxygen is less electronegative, but this negative charge here is even weaker because of resonance.
Gotcha.
Whereas nitrogen here is like no resonance at all, which makes it less stable, more reactive, making it a stronger base. Right. So you are technically correct. This O minus here can be used to deprotonate the nitrogen intramolecularly, but it's gonna happen 1 out of like 100 or 1,000 times, right? Because the other 100 or 1,000 times, the amine is gonna be the stronger base that overpowers the carboxylate as a base. Right. Yeah. Okay. And this H plus workup right here has to be dilute, like in low concentration, to just protonate the O minus. If we have like a highly concentrated acid right here, we're also going to protonate the nitrogen to make it positively charged like that. So that's why we call it H plus workup. Workup meaning that dilute enough just to neutralize the minus charge, just to clean up the solution and neutralize it. Okay. Any other questions? Okay. Do you guys want a quick rundown of all of chapter 21, or are there any like specific parts of chapter 21 you guys want to go over? Because I can like go over all of chapter 21 as well in like 30 minutes or so.
Can you do the whole chapter? I'm so sorry.
Okay. The whole chapter? Let's do the whole chapter.
Thank you so much.
Yeah, Let's do it. So chapter 21 is going to talk about the amines. Right? And the first thing that we're going to do is talk about Well, first, there's a lot of things going on. There's nomenclature of amines. There's basicity of amines, acidity of amines. I'm gonna focus on the reactions and mechanism of amines, and then if you have time, I'll go over like the other like more straightforward concepts like nomenclature, basicity, acidity, and their properties. Right, but I'm gonna focus on the reactions first. Okay, so let's look at the preparation of amines. So there are a few ways that you already know how to do this, which is going to be the reduction of nitrile, right? And then I'm going to compare that to the reduction of azide versus azide. Let's say that we have this primary haloalkane and we react it with NaCN versus NaN3. The NaCN is going to do an SN2 reaction, substituting the bromine with a nitrile, CN. The NaN3 is going to substitute the bromine with the azide, N3. The biggest difference between these two is that the nitrile added an extra carbon, right? Because if you look at the reactant molecule, we started with 3 carbons, but when we used NaCN, we extended the carbon skeleton by 1 carbon, right? Before we had 3 carbons in the carbon skeleton, but now we have 4 carbons. The 4th carbon is coming from the nitrile carbon. When we use azide, however, we maintain the same carbon skeleton. We didn't add a carbon, we didn't lose a carbon. So once we have the nitrile and azide, we could reduce it using lithium aluminum hydride, H plus workup, lithium aluminum hydride, acid workup, and reduce it to the amine, NH2. NH2. The most common mistake that students make for these reactions is the carbon skeleton like length, right? If you use the nitrile, be sure to add the extra carbon from the reactant molecule. If you use an azide, be sure that you maintain the same carbon skeleton length like that, right? So that's one way that we could do to prepare amines. The other way is going to be SN2 with amines, right? Let's say we have this haloalkane and we want to create a primary amine by putting, let's say, ammonia to it. Let's say NH3, right? This ammonia right here is going to be the strong nucleophile. This is going to be the electrophile, the dot. The nucleophile is going to be the star. Star attack the dot, kick out the leaving group. And we're going to have this new bond between the star and dot. Star, dot, right? New bond between the nitrogen and carbon. This nitrogen here, or the star, has 3 hydrogens attached to it still. So because this nitrogen has 4 bonds, it's going to be positively charged, right? Because if we calculate the formal charge, nitrogen is in the 5th column, 5th group. It wants 5 electrons to itself. But it has 1, 2, 3, 4 electrons. 5 minus 4 is positive 1. So that's why this nitrogen has a positive charge with 4 bonds. And we can neutralize that positive charge nitrogen with another ammonia instead of a Br minus, because think of this ammonia as an excess in the solution. We have 1,000,000 times more ammonia molecules than the bromine minus, making this ammonia be the stronger base that would deprotonate the positive charge nitrogen, right? Another reason is that this negative charge here is like stable with the extremely electronegative halogen, right? Whereas nitrogen is like not as electronegative. It's more willing to donate its electrons to deprotonate and neutralize the nitrogen, right? But when we did that, we gave this nitrogen another pair of electrons, which is nucleophilic, right? So we also have excess amount of haloalkane. So we're going to bring in another equivalent of haloalkane and attack again and do another SN2 reaction. Right, 1, 2, 3. which gives us nitrogen positive charge again. So we're gonna keep doing this, like acid-base reaction, SN2 reaction, until we can no longer deprotonate the nitrogen, until we can no longer neutralize the nitrogen. Right, so I'm just gonna keep going, boom, boom, make it neutral. Right, and then because it has a pair of electrons I could attack, it's gonna attack another halocane here, kick out the leaving group, and 1, 2, 3, hydrogen, positive. Now this is the last step here. Ammonia is going to deprotonate. This is the last acid-base step, I mean, because once we do that, this nitrogen becomes nucleophilic again, which is going to attack another halocane, which this is going to be the last step now. Because once we do that, we're going to get this quaternary ammonium ion, where we can no longer neutralize the positive charged nitrogen because there's no protons left to grab and deprotonate. Right, so this is over-alkylation of amine. And this is a big problem in lab or synthetic purposes, because let's say we want to end up with a primary amine or a secondary amine or even a tertiary amine, right? We don't want to like get this weird quaternary ammonium ion. So this is a bad synthesis reaction, right? A bad reaction to do in lab. A better reaction would be reductive amination. Reductive amination. So this is gonna have a aldehyde or a ketone react with either ammonia, a primary or secondary amine, in acidic conditions. And the second step is going to be a new reducing agent that you are going to see in this chapter, NaBH3CN, to create some kind of amine. And I'll show you what that means here. Right. Let's just say I give you this generic ketone, and I give you guys these 3 different reagents here. The first one is going to be ammonia in acidic conditions. Second step, NaBH3CN. The second reaction is going to be a primary amine in acidic conditions. Second step, NaBH3CN. The third reaction is going to be a secondary amine in acidic conditions, NaBH3CN. Right. So this is going to go back to 1,1-B. I don't know who you guys had for 1,1-B. Like, if you guys had it with Mascal last spring, or who was the professor last summer session? Ling. He had Mascal last quarter. Yeah. So, do you remember this reaction right here? Like when you have, it's okay if you don't, because it's been a long time. When we react the carbonyl with like some sort of amine in acidic conditions, it forms a really weird structure. It starts with an I.
And was it an amine?
Yep, imine, right, with an I, right? So it's gonna create an, because we're in acidic conditions, it's gonna be protonated. So it's gonna have an iminium ion, right, like this, because we are still in acidic conditions. So this is the first step right here, where what we just basically did is substitute the carbonyl, the carbon double bond oxygen, with the amine minus 1 hydrogen, right? This carbon is now double bonded to this nitrogen right here. But before it used to have 3 hydrogens, now it has 2 hydrogens like that. This is an iminium ion. We don't have to worry about the mechanism for this, because I highly doubt that this is going to be on the exam. The high yield mechanisms for this exam is going to be the chapter 1921s, especially the nucleophilic acyl addition elimination, like Fischer esterification, trans esterification, and all the hydrolysis reactions from the derivatives in acidic or basic conditions, right? Those are going to be the most likely ones, which can be tricky if it's intramolecular, right? Like if you're forming a ring, or if you're breaking apart a ring in hydrolysis. So focus on the chapter 1920 nucleophilic acyl addition elimination mechanisms. That's the big mechanism part. Right. But for these reactions right here, just know that you're going to make this iminium ion in the first step, and the second step with the NaBH3CN is going to reduce it into an amine like that, right? We get rid of the double bond and neutralize the positively charged nitrogen like that. The reason why we use NaBH3CN as a reducing agent instead of the other reducing agent like lithium aluminum hydride or sodium borohydride is because this NaBH3CN here is a weaker reducing agent than these two. So if there was a ketone present, right, and we only wanted to reduce the iminium ion into the amine, we would have to use the NaBH3CN, right? Because NaBH3CN is a weak reducing agent, which is only weak enough to reduce the iminium ion into the amine. If we were to use lithium aluminum hydride or sodium borohydride instead, we would reduce both the iminium ion and the ketone or aldehyde down, right? But in synthesis, if you don't want to reduce a ketone or aldehyde, you have to use NaBH3CN. And you'll most likely see this as a reagent for predicted product for reductive amination. This reducing agent right here, NaBH3CN, is a big indicator that you have a reductive amination reaction going on. Would we be able to use H2PD as a different kind of mild reducing agent? Yes, you can use H2 PD as a mild reducing agent as well, but you have the potential of also reducing like an alkene or an alkyne if they're present, right? So an H2PD can also reduce these as well. But NaBH3CN would not reduce the alkene or alkyne. So it's best if we use NaBH3CN for the reductive amination reaction. Right. But I like that you're thinking about the other reducing agents that you could use, like H2PD. But we also have to think about like what those reducing agents can reduce if they're present. In this molecule here, it didn't really matter, right? We could use any like of the reducing agents we talked about. We could use lithium aluminum hydride, sodium borohydride, NaBH3CN, or H2PD, and we would get the same product, right? But just to be like consistent, we use NaBH3CN usually for reductive amination. But this is why understanding like the mechanism is really important, because sometimes professors switch things up and they use another reducing agent, and then you're like, what the heck is going on here? I've never seen this before. So that's why like you gotta know like what's what, like what's the nucleophile, what's the electrophile, what's being reduced, what's being oxidized, right? When you see a reducing agent, you ask yourself what's being reduced and like why that's being used instead of the other ones. Why wouldn't the NH3 react with the acid in the first step? Yeah, so that's a good question. Oh my god, these are actually very good questions, like conceptual questions. So NH3, right? This is more of a Neissery class thing, which helix and Levens, they don't do this, right? The H plus, Levens and helix usually just protonate the carbonyl oxygen first, activating the carbonyl, making it a stronger electrophile, right? But what actually happens is what you say, what you just said. Because this amine right here, the nitrogen, is more basic than the carbonyl oxygen, this amine right here is going to get protonated first. So that's going to happen first, actually, like you said, right? And when that happens, our proton source, our acid source, is now this ammonium ion, this NH4 plus, where that's going to be the acid source for this carbonyl oxygen to get protonated, right? So the hydrogen source is coming from this ammonium ion rather than the H plus source, right? So it's like we're protonating the amine just to get the ammonium ion, which will act as the acid for this carbonyl. And then when that happens, we are going to get this protonated carbonyl, activated electrophile, and neutral amine here. And then the neutral amine is going to attack the activated electrophile and pop that up there, like that, right? But Levens and helix, they just go straight for the H plus from the carbonyl oxygen to go straight to here right away. right? But Nasiri does this route where she protonates the amine first, and then the protonated form of the amine is the acid source for the carbonyl oxygen, like that. Right. Farahat, I'm not sure, but since he follows the textbook, I think he's gonna like be more of a like Nasiri. So I think he would want this way as well, like protonate the amine first, and then use the protonated amine as the acid source for the carbonyl oxygen. Right. Okay. So using a primary amine, we're gonna do the same thing. Substitute the carbonyl with the amine minus 1 hydrogen, which is going to give us these iminium ions. And then when we do Na-BH3CN, we're going to reduce that iminium ion into this neutral amine here. The difference between ammonia primary amine and a secondary amine is that a secondary amine is not going to create an iminium ion. It's going to create an enamine. That, right? So well, actually, because we're in acidic conditions, you can work with either the enamine or its iminium ion form. Right? Because we're not trying to get to the neutral product. Using either one of these, if you reduce it with NaBH3CN, you're going to get this neutral amine here. Right? Where the overall reaction substituted the carbonyl with the amine that we used, minus 1 hydrogen, right? Notice how we substituted the carbonyl with the amine on the reagent, minus 1 hydrogen. That's what this reaction overall did, reductive amination. This reaction would not work with tertiary amine because it's going to be like the mechanism, the intermediate can't be deprotonated and neutralized, right? We need at least 1 hydrogen to take away for this reaction, right? The secondary amine here has 1 hydrogen, which we took away, which is why we don't see any hydrogens in the product there. Okay, so any questions on reductive amination? Okay, let's go over Gabriel synthesis, the other way to form amino acid. I mean, not amino acid, amines, Gabriel synthesis. But this we actually will go back when you learn about amino acid chapter 25 or 6, chapter 26. Okay. So Gabriel synthesis, know these molecules, phthalic acid, which is a dioic acid, and when we put NH3 excess in heat to it, we're going to merge them together to create the cyclic amide. This is a chapter 20 reaction here, or chapter 19 reaction here. Right, carboxylic acid to amide using ammonia with heat. This heat is the point right here, because if you just had ammonia, that ammonia is just going to deprotonate the carboxylic acid to get the carboxylate acid-base reaction. Right. Once we have this structure is called the phthalimide. I don't know if I'm spelling this correct, phthalimide, but yeah, so something like that. Right. Once you have this phthalimide, this hydrogen here is acidic. So when we introduce some kind of base to it, like KOH, the OH minus is going to deprotonate the nitrogen to give us this negatively charged nitrogen here. Right. Which this is going to be a good nucleophile. So think of this as your nitrogen for your primary amine that you're going to create soon. We can introduce any kind of haloalkane for SN2 reaction. Like let's say this haloalkane right here. This nucleophile is going to attack that electrophile, kick out that leaving group to give us this intermediate here. This is an SN2 reaction here. So To keep track of all the atoms, I like to use this technique, the star and dot technique. I star my nucleophile, I dot my electrophile, and I make a new bond between the star and dot. Star, dot. This is the new bond between them. And I do this to be sure that I don't add an extra carbon or lose a carbon by accident, right? The dot here is attached to a CH2 and isopropyl like that, okay? Now, once I have this, I want to do hydrolysis, H3O plus H2O heat, which is going to cut these bonds, make a carboxylic acid again, the dioic acid, and this part of the molecule here, think of it as the leaving group, is going to be my amine, right? So I've seen this on your achieve homework. Because we're in acidic conditions, the amine is going to be in protonated state, right? It's going to have a positive charge because it's going to get protonated. If you want to get the neutral form, you have to add a second step of base, NaOH, in water, just to deprotonate and neutralize the amine, like that. Right, so that's Gabriel synthesis, forming a primary amine here, and the phthalic acid again. Okay, what other ways to form amines? Reductive amination. Okay, I want to go over Hoffman elimination with you guys now. So we're moving away from preparing amines into the actual reactions with amines now. Hoffman elimination, which is one of them. You guys are already familiar with Hoffman rearrangement, right? That's different than Hoffman elimination. Right. Actually, just for a quick recap, Hoffman rearrangement. So just because of time, right, I plan on completing chapter 21 tomorrow, which is going to talk about the bigger reactions like Hoffman elimination and Mannich reaction, and show you guys shortcuts on how to predict the product and how to go backwards from synthesis. Like if they give you a product of these reactions here, how to go backwards, how to break it down and go backwards as well, because this is going to take a longer time. These reactions, Hoffman elimination, Mannich reaction, and diazonium salt or nitrosamine formation, nitrosamine, right? But we'll end off the session with Hoffman rearrangement and any other questions you guys have that I could work through. But these reactions would take more time, so I'll do these tomorrow at the beginning of the session. So Hoffman rearrangement is a chapter 20 reaction, but this ties back into chapter 21, which is going to have a primary amide reacting with Br2 NaOH and water to create a primary amine. And the most important feature about this reaction is that we are removing one carbon from the carbon skeleton, right? And that one carbon that we are removing is going to be the carbonyl carbon. And I'm going to show you an example of it right now. So let's say I have this primary amide right here, right? And I give you guys these reagents, Br2, NaOH, and water. I'm going to substitute this whole amide into this primary amine here, NH2. And notice how this carbon here is now gone. It went poof, it went away, right? And it goes away in the form of carbon dioxide, CO2, right? So that might be a conceptual multiple choice question in Hoffman rearrangement. What happens to the molecule? Like what gets formed, which is a primary amine and carbon dioxide, right? The carbon dioxide carbon is the amide carbon here. Okay, so Any questions on what I just did over here? I know I kind of rushed it, but any questions so far? If not, I'll give you guys practice problems on what we just did to reinforce these concepts. Okay, so okay, let's see what we just did. Okay, I'm gonna give you guys a predicted product problem and a synthesis problem to try out. Okay, let's say we have this reacting with this, H, this step, step, H, water. Try this multi-step predicted product problem. And for synthesis, let's try this. Okay, let's see here. And I'm going to use chapter 19 and 20 reactions as well, just to combine 19, 20, and 21 together. Let's see. I'm going to work it right here. Okay, can you please explain the reaction of CH3, CH2, CN plus 1 benzene, MGBr, ether, second step, acid work when you get plus. Oh, I see what you're talking. Yeah, okay. H3O plus. Okay, try these two problems. One is the predicted product multi-step problem. The second one is a synthesis problem. Right? While you guys work on these, I'm gonna go through this problem here. So this reactant is a nitrile, right? And the nitrile has a triple bond between the carbon and nitrogen. This carbon here has a partial positive charge because it's bonded to an electronegative nitrogen atom here. Right? The nitrogen is more electronegative than the carbon is, which is why this carbon is partial positive. In the reagent, our first step is a Grignard reagent, right? And in Grignard reagent, the very first atom attached to the magnesium is partial negative charge. And a way that you can think about this is that carbon is more electronegative than magnesium, making carbon partial negative. This carbon here that's partial negative makes it the nucleophile, right? Nucleophile is nucleus loving, and the nucleus is positively charged because it has protons. And if it loves positive charge, it has to be negative charge itself. Right? A nucleophile has to be negative charge because opposite charges attract. This carbon here is our electrophile because electrophiles are electron loving. They love electrons. So if they love electrons, they have to be positively charged, right? Because opposite charges attract. So in reactions, nucleophiles always attack electrophiles, not the other way around, right? Because the things that are moving are the electrons. The electrons are the ones that are attacking something positive, right? So negative charges are always going towards positive charge. So this nucleophile here, or the star, right? I starred my nucleophile, I dot my electrophile. This star here is going to attack my dot, pushing one of the bonds of the triple bond onto the nitrogen like that, right? Because we're trying to make a new bond between the carbon here and the carbon here. But this carbon already had 4 bonds. So if this carbon has 5 bonds, that's going to break the octet rule. To conserve the octet rule, we have to move one of the bonds, which is going to be one of the bonds of the triple bond, onto the nitrogen right here, right? And when we connect these two together, CH3CH2. I see. Okay, so I don't think you need to know the mechanism for this, but I'm going to show you anyway. But after I show you the mechanism, I'm going to show you the shortcut, right? And this table here that I would recommend you guys to use. When that happens, this is my star dot. This is my star right here. This star is part of a benzene ring, which is this benzene right here. This dot carbon is now double bonded to a nitrogen that's negatively charged, right? And then yeah, I remember this from the Achieve homework. This N minus here is going to get protonated by the hydronium ion to get us this neutral imine here with the I, right? So once we have that imine right there, if we are still in acidic conditions, we're going to do hydrolysis of imine into carbonyl. I don't think you guys need to know about this mechanism, so I don't want to overwhelm you guys with too much information. But know that if we have an imine and we're still in acidic conditions, H3O plus, water, and something like that, if water is present especially, we're going to hydrolyze the imine into the carbonyl like this, right? So this reaction here was a nitrile plus Grignard reagent reaction, right? Where notice how, here's a shortcut now, we're always going to make a ketone, a nitrile plus a Grignard reagent. In the first step, second step, acid workup, is always going to give you a ketone. Right, so that's a shortcut. Where the ketone carbon is always going to be the carbon of the nitrile. Because notice how this ketone carbon right here, that yellow highlighted carbon is that yellow highlighted carbon right there. This ethyl group is that ethyl group right there. The other R group, the other part of the ketone, is the R group of the Grignard right there. So that's how you can predict the product quickly. And I'll show you guys a table tomorrow of the reduction reactions and organometallic reactions with all the derivatives after we finish chapter 21, just to complete chapter 19 and 20 reactions, right? But this is the shortcut for reducing nitrile. I mean, reacting a nitrile with a Grignard reagent, organometallic, right? Which is always going to create a ketone, where the carbonyl carbon of the ketone is the carbon of the nitrile, and the new R group attached is the R group of the Grignard, organometallic. Okay. Did anyone get the first problem here? Okay. So the first, yeah, okay, yeah, Peter. Would you like to try explaining what you got? It's okay if you get it wrong because like we could fix the mistake and prevent it on the exam.
Yeah, doesn't it just follow the same structure as our halo alkane, except the Br is replaced with an amine, and then your
Yeah.
side product is um the philothath phil I can't pronounce it,
Yeah,
acid.
yeah. Right. That's correct. Uh-huh. Right. So Peter pointed out a good way to predict the product quickly. When you see this phthalimide, that weird structure, this is a big indicator for Gabriel synthesis, which is one of the ways to make amines. And Gabriel synthesis always forms primary amines, right? And the primary amine here is going to be like basically that halocane, but substituting that bromine with that NH2 right there to get the final product. And this right here would be our side product, which I would still include in the predicted product in the box. But Farahat, I heard his exams is mostly multiple choice, so I don't know how that's gonna work. It might be like what products get formed, and then he might like explain it by name or picture. I'm not sure, but this might be important as well to include in the answer. Yeah, that's good. Nice. Uh-huh. Okay, so synthesis. Has anyone tried the synthesis film and able to get it? If not, what did you guys try to do at least? Yeah. Yeah. Go ahead, Peter.
So I don't know if this is right. It kind of made sense to me though. So
Yep.
initially I added ethylamine with acid, followed by sodium borohydride with a CN. And so that takes care of the ketone, making it into the secondary amine at the bottom there. And then I
That's right.
added SOCl2, which would make a better leaving group for the instead of the carboxylic acid. But then after that, I added NH3 to make an amide.
Yep.
And then
Right.
after the amide, I used the Hoffman rearrangement by adding
Yes.
Br2 and AOH to remove the carbonyl.
Yes.
Oh,
Yeah. That's good. That's good. You got it.
thank you.
And you got NH3 excess, no heat needed because it's an acyl halide. Get this amide. The amine still there, and then we see that this carbon here of the amide is no longer there, -1 carbon. Big feature of Hoffman rearrangement, which gets rid of that amide carbon. So we use Br2 and AOH, H2, the Hoffman rearrangement reagents. Originally, I thought of doing the SOCO2 route first to do the Grignard reagent because the order matters here, right? So depends on the professor and how like picky they are. This first step, amine right here with acidic conditions, you were trying to do reductive amination with the carbonyl with the NABH3CN, but in acidic conditions with amine, wait, actually, no. I just realized. Yeah, this will still work. Yeah, right. Yeah. Because I was gonna say this carboxylic acid here could have reacted with the amine to create an amide, but that won't work because once the amine gets protonated to get that protonated amine form, this amine right here has no more pairs of electrons to attack the carboxylic acid so it can create the amide there, right? But this can be the acid source for that ketone and do the whole reductive amination, creating the secondary amine here. And then we do the SLCO2, acyl halide, create the amide, get rid of that carbonyl carbon, convert the amine into amine there. Nice.
So for that situation that you proposed with saying that it won't do a nucleophilic attack there, why wouldn't it protonate the carbonyl and then do the nucleophilic attack when it's back to the NH2?
Like for this one right here.
Yeah.
Right. So it can do that. Like this carbon oxygen can deprotonate that, creating the NH2 again, making this activated.
Mhm.
And then doing that whole thing to get the amide, which if we did create the amide, then we could use that amide to do the Hoffman rearrangement right away to get to that final product. So that's the other way you could do that as well.
I see. Okay,
Yeah,
thank you.
right. I kind of just made the synthesis problem on the spot, but now like working through it with you, I just realized like there's multiple ways that you could do this. Right, like that's good that you found that as well. Right. Yeah, that's good. That's good. Where the first step, like the route that you proposed at the beginning, we did reductive amination first, and then acyl halide formation, specifically acyl chloride formation. If you wanted acyl bromide, you would use PBr3. And then we did amide formation. And then we did Hoffman rearrangement. Can you explain why NaCN reduction does not work to convert the carboxylic acid? NaCN reduction. Like convert the carboxylic acid to this amine right here. Yes. Oh, like why can't we? Oh, are you saying like we can do reduction like LiAlH4 second step H plus to get that amine with the nitrile, but the nitrile would have to look like this. CN, like that, right? And to get to this CN right here, we would have to first convert this carboxylic acid into the amide, the primary amide, like that. And then to convert the amide into the amine, we use SOCO2. SOCO2, like that. Right? Where this carbon of the amide is that carbon of the CN. And then to create the amide from the carboxylic acid, we're going to do first step SOCO2, second step excess ammonia. Right? So we can do that way too, Ryan. But we would have to go this route, right? Including the reductive amination as well. Right? If you wanted to get this amine from the reduction of nitrile, right? But to get to the nitrile, you would first have to get to the amide. Yeah, so that's another way too. Dang, so many ways. I didn't think about these. You guys have got a lot of tools in your toolbox already. A lot of reactions you guys know that you could do. Like that's so good. Okay. So I'm gonna end office hours here. How did you guys like? I mean, like I've never seen you guys before. Like where'd you guys come from?
I actually found your YouTube over the summer. And
Uh-huh.
and then I told a few of the people here, actually from my end, I told them because we've all been like struggling with
Oh.
the material on our own. And then I watched your midterm one review video from spring, I think. I think it was for Helix. And it was for
Yeah.
chapters 19 and 20. And it was so like it
Uh-huh.
was because usually it depends on the book. And then I watched your video. And I was like, this is so much better than the book. And so I texted
Oh
you. I
my
was like,
God.
can you please go over 21 in your office hours tomorrow?
Yeah, I see. Oh my God. Dang, that's crazy. So like everyone here are your friends that you invited them over, like Peter, Raimi,
Oh, not
Kuro.
everyone, but like a few of them. Yeah. Peter
All
is,
right. I
yeah.
think Brooke is from Camilla. Yeah, Camilla from Brooke.
Yeah, Rund invited me and Rami.
Yeah, I see. Dang. Oh, I see, Kuro. Dang. Okay.
I love that.
Yeah. Okay. And Ryan, we gotta finish up our sessions. Yeah, I'll see you guys tomorrow if you guys plan on coming tomorrow. Good
Is
luck.
it same time, same
Thank you,
link?
Brian.
Yep, same time, same link, 9 to 10 p.m. The same link.
Okay, great. Thank you so
Yeah.
much, Brian.
Yeah. No problem.
Brian,
Yeah.
I'm sorry, I have like a quick question. Sorry, can you hear me?
Yes, I can hear you.
Okay. I was trying to book a couple of sessions, right? But I saw that you were
Yes.
booked all the way and not until after the midterm. So I was wondering if there's any way that, we could have maybe like a 2-hour session before. Is that possible?
Right, because okay, so let me check my calendar really quick.
Okay.
This our session before the midterm. See, let me stop.